Hello, Dr. Mo. So on this slide, we're just going to go over the rationale for this assignment. So we're looking at how do we produce the vowel, a vowel ah is the vowel that we chose, and the M sound. So in this slide, we're going to go over kind of what we're going to be going through over the consequential slides. So the description of the whole process for a vowel, which is ah, and then we'll describe the process for an M sound. So before we go into the actual production of the difference between an ah and an we first need to have an understanding of how sound is actually produced. So sound occurs when a disturbance creates change in pressure in a gas, liquid, or solid. There's a couple different things when talking about sound that we need to take into accommodation here. So we need to talk about pressure, equalization, driving pressure, what the actual airflow is, and Boyle's law, which is super important with how we produce sound. So with pressure equalization, that's when hyperactive air molecules move from high to low pressure to equalize. And then for the driving pressure, this is created from air molecules equalizing, which is crucial in generating speech. Airflow, which is very important in sound production because that all kind of determines on what's happening, especially between the oral cavity and the nasal cavity. We want to know where the air is flowing through which of those cavities. This is the movement of air, again, through a particular cavity over a certain period of time. And then Boyle's law, this is an inverse relationship between air volume and pressure, which creates a perfect storm for speech. This is super important, especially at the glottal pressure right underneath the vocal folds, which we'll dive into in just a little bit. With resonance, this is a very big topic when talking about just vocal production in general. So now that we have an understanding of how the sound is actually produced, we want to talk about how that sound is actually coming towards the surface, and resonance is a big part of that. So what is resonance? I feel like a lot of people get confused on what resonance actually is. What it is a system to vibrate with the greatest amplitude in response to a frequency that matches or comes close to its natural frequency. There's four big players that come into play to help determine the natural frequency. That's the length, the density, tension, and stiffness. With those four players, this is a really big deal when talking about vocal disorders and speech disorders, especially when talking about dysphonia. You can have length, density, tension, and stiffness, which again has a different natural frequency for that person with the speech disorder, which causes them to have a different resonance because their frequency is different. So you can see how the relationship works together. Also, when talking about natural frequency, you want to look at vibration essentially in that system. So there's two different types of vibrations that occur, and one of those is forced vibration, the other one is free vibration. So what are the difference between those two? Forced is basically when there is an outside source that comes to create a vibration in that system. Free vibration is essentially that system to be able to vibrate with its own natural frequency. So again, the four big players that we want to remember with resonance is length, density, tension, and stiffness. Now that we have an understanding of what resonance is, we want to talk about what an actual resonator is. So resonance and resonators do kind of go hand in hand together, but there is a little difference between the two. So there's two different types of resonators that deal with resonance. You have an acoustic resonator, and then you have a mechanical resonator. So when people think acoustic, a lot of times most people think about a guitar. So it's a volume of air enclosed in a container that can resonate. So with a guitar, it has its own cavity with an opening, and then when you strum the strings, that's when you can get the acoustic sound that comes through the guitar sound. The next resonator is a mechanical resonator. So this is where the object itself is set into motion. An example of a mechanical resonator, some people would say that this would be the vocal system, because in order to create sound, we have to have some sort of object itself where it sets in motion to create sound. But actually the vocal system is both, because you do have those air enclosed containers, so those cavities that are able to resonate, which helps with the production of sound. So when talking about resonators, one great example of that we talked about in class especially are the Helmholtz resonators. So what these are a scientifically evolved special capsules. Each one of them have their own natural frequency. These are an example of quarter wave resonators, which we'll talk about in just a little bit, explain and expand more on that. They're actually a great example because they're very similar to the vocal tract by having one end open and the other closed, as you can see in this picture. And they're also very similar is that they're an air-filled space. So think about if you were to blow on a Coke bottle and kind of the sound that comes out of there. That would be very similar if you were to use these Helmholtz resonators, because each one has their own specific natural frequency, just like a Coke bottle were too as well. So in this picture, these ones are metal. Doing some research, I didn't see any ones that were plastic, but these are a great example to kind of think about how the vocal tract actually works with the nasal cavity, the oral cavity, pharyngeal, laryngeal cavities, and how air is kind of moving and creating that frequency and resonance. So once again, we're just going to hit on a few extra points about an acoustic resonator, because it's very important, especially with the production of sound. So some things to point out that make it a little different from a mechanical resonator is that it filters out some sound while permitting other sounds to remain because of density. So again, if we think about our guitar example, by having that cavity in the strings, it's able to permit some sounds come out but others not to. And a big difference with that is you can hear basically when a guitar is in tune or out of tune, because depending on how the string is tightened or lengthened gives a big difference between sound. With acoustic resonators, it amplifies frequencies closest to the resonating frequency. And the last thing is attenuates, which prevents away from resonating frequency from being transmitted. So again, just some extra notes on acoustic resonators, because when we think about the vocal tract and how we have sound production, acoustically is a very large part in the production of sound. So when we're thinking about resonators, we want to talk about a quarter wave resonator, which is a very important point when talking about how to produce sound, and also in the vocal tract. So in the vocal tract, it's a quarter wave resonator because in our vocal tract we have one open at one end and it's closed at another. So how you can think about that, it's with our articulators and the source filter theory. With our vocal folds, they're always moving back and forth. But at some point, we do always have one end open and the other one closed. A quarter wave resonator it's called a quarter wave because one quarter of the wave fits in the resonator at a time. So if you were to draw out a wave in the tube when we're talking about a resonator, a quarter of the wave is going to fit in there between the open and the closed end. So again, this is super important when talking about the vocal tract, because that's the type of resonator it is a quarter wave resonator. Alright, so now that we have taken a look at what a resonator is, what resonance is, those are just kind of two parts to the whole. So the last thing that we need to talk about to bring all of those pieces together to create our whole piece of pie is resonating frequency. So what is resonating frequency? It's a rate determined by its physical characteristics. So again, the four main players that we talked about previously: length, density, tension, and stiffness. Those all together create have a vibrate at its own specific frequency with resonating frequencies. These are often known as formants, because with formants, this is especially important when we're talking about vocal production. This is where we can actually see what is happening on a spectrogram to be able to tell the difference, for example, between a vowel and a consonant. So it's super important that we have an understanding of what a resonator is and what resonance is, but it's also very important to have an idea of what a resonating frequency is, because that's something that we can actually see and can tell the difference between vowels and consonants. So now that we've gone over what a resonator is, what resonance is, and what a resonator frequency is, we're going to talk specifically about vocal tract as a resonator. So with the vocal tract, as mentioned before, it has resonating cavities that change and vary in shape in the vocal tract. So the cavities that I mentioned before is the pharyngeal, the oral, and the nasal cavity, and those can vary in shape to create different vowels and consonants. So next we talk about the movement of articulators. So the articulators, for some example of those, are the tongue, the velum, the lips, and the jaw. So with the articulators, these can changes the shape, variety of speech sounds. It creates, it filters to transmit frequencies. So again, they have difference in the resonating frequencies. The sounds produced by the larynx are within the vocal tract. So with the articulators, it can change all of those points to create a different frequency, and that's why the vocal tract is a resonator. Hi guys, so on this slide we're going to talk about basically how the lungs is kind of a separate, basically it's a system of different valves. And so here at the bottom we have the lungs that you guys can see, and then next we have the laryngeal valve, the pharyngeal valve, but also we have a lot of air space filled cavities. For example, we have the nasal cavity, we also have the space in here, the pharyngeal cavity, the laryngeal cavity, also the oral cavity as well. So you guys can see that there's a lot of different air space filled cavities that air travels through, and that's how we can manipulate this to get our different sounds. So when it comes to the lowest sound available, which is our F0, as you can see right here, that basically starts right below the laryngeal valve, or the vocal folds coming up from the lungs, and then once it passes through that valve right here in the pharyngeal, in between the velopharyngeal valve and the laryngeal valve, you have your F1, so this would be your first formant if you were looking at a spectrogram. And then for the example, we'll use an ah. Then you have air that's moving through here, and that is a low back valve or sound. So your F2 will be right back here, and then your F3 is kind of when the sound is coming out into the oral cavity through to the outside world. With the ah, your bilabial valves are open, versus an M, it would be very similar, except you're having sound going through the nasal cavity, and also your bilabials are closed, so it'd be a little different route that it would take. So you would have your F0 again underneath your laryngeal valve. Your velum would be open, which allows air to go up through the nasal cavity. So your F1, F2, and F3 would be a little different up in this area. Thanks guys, have a great rest of your day. So good. Hold on. I'm trying to figure it out. So before we get into the difference between the ah and the sound, we need to have an understanding of what vowels versus consonants are like. So things to keep in mind: the vowel of sounds with a vocal tract plays a big role in sounds we create and classify, which we've been talking about through previous slides. So hopefully that concept should be drilled into the brain right about now. So a big thing, the difference between vowels and consonants that we take a look at is the manner of articulation versus the place of articulation. So the manner of articulation is how the configuration and integration of the articulators works. So that's basically how we help classify consonants and vowels. The place of articulation is where things are actually occurring in the oral and nasal cavity. So basically where our articulators, so the tongue, the teeth, the lips, the jaw, how those are all moving to create a certain sound. So when we're talking about sound production, as we mentioned earlier, airflow is a very big deal in the vocal tract to produce sound. So we have two different types of airflow. One of those is laminar airflow and the other one is turbulent airflow. So with laminar airflow, that's essentially just kind of the breeze kind of moving through slowly. It's just very fluid and simple. Turbulent airflow, there's a lot more going on. So an example between those two, with a vowel, that would be more of a laminar airflow. Things are just kind of flowing. So when you think about the ah sound, ah, air is just kind of flowing out of the vocal tract with the movement of the articulators to create those vowel sounds. Now, with consonants, there's definitely a lot more turbulent airflow going on. So an example with the sound, you'll have more articular constriction, creating that turbulent airflow. Another thing to think about is fricatives. There's a lot of turbulent airflow going on with those fricatives as well. So now that we've talked about basically how do we get sound, we've talked about the articulators, we haven't talked about the overall theory that is concerned with all of these things that we've talked about in the previous slides. So the theory that we're going to mention here is the source filter theory. So what the source filter theory is it's going to be divided really into three components, which takes a look at the source, and then it takes a look at the filter, and then actually what is coming out. So the first is a source. So the sound from the glottis that goes through the vocal tract. Sound comes from the glottis before it is resonated and it sounds like a buzz. So this would be your formant frequency. So this would be your F0, so kind of what your baseline is. So if we didn't have our articulators to shape our different sounds and productions, it would just sound like a buzz that we would have coming from the vocal folds. Next, we're going to talk about the transference of the sound through the vocal tract. So this is how we have different frequency responses. So when we're thinking about all the different vowels and consonants that we have in the English language, a lot of those have a very different frequency associated with that. So if you think about S, that has a very high frequency versus a nasal, which has that's a lower frequency. So as you can think about those different sounds, not only in the English language, but also languages around the world, that's a very big difference. Next, so that's when we talk about the filter. So those different filters that we use in our vocal production, you can use those. Next, we're going to talk about the output function. So what is actually coming out? This is the emergent sound from the lips, or it could be from the nasal cavity. So there's just a lot going on here. So the sound produced in the glottis is the same fundamental frequency and harmonics, but has changed due to the amplitude of the harmonics. Sound has been filtered from its source according to the frequency response and resonance of the vocal tract. So basically, when we look at the output, we can not only see the difference between vowels and consonants, but we can hear the difference as well. So you're able to see kind of how all the terms have come together to create the source filter theory, which is very important in sound production and vocal production of certain vowels and consonants. So now that we've kind of given you the background knowledge of how sound production and vocal production work, we're going to talk about the main attributes to what this assignment is. So we're going to talk about the difference between the ah and the sound production process. So first we'll start with the ah, which is the vowel that Kaileigh and I decided to choose. So when we're thinking about the ah sound, we need to think about the glottal pressure, which is underneath the vocal folds, and this is going to help us with the understanding of the source filter theory. So this is the source. So as air moves from high to low pressure towards the articulators, this is the transference part of the source filter theory model. Next, we're going to talk about the articulators. So what is actually happening with the ah production with our articulators? The velum is closed. That way we don't have any air going through the nasal cavities. So the vocal folds are chopping air as it's moving from high to low pressure. Next, the pharyngeal cavity is open and the oral cavity is open. So when looking at the ah, it is a low back vowel. So that's our output function in the source filter theory. So as we're looking at output with the articulators, our tongue, teeth, palate, and lips are also relaxed. So there is just a relaxed form in the oral cavity for the speaker, which creates a resonance, and that's how we get the sound production of ah. So it's a very easy vowel to produce. Again, it'll look very similar across all speakers, but that's when we take all the terms that we've learned throughout the slides, putting it all together with source filter theory, you can see how an ah is produced. So now that we've talked about the ah sound production process, we're going to talk about the M. So now that you kind of have the background of how the ah works, it's very similar, but it also has some differences between the vowels. So an M is a consonant. So again, you'll still have the same source, so the glottal pressure underneath the vocal folds. Next, again, very similar as air moves from high to low pressure towards the articulators. This is the transference in part of the source filter theory model. Next, we're going to take a look at the filter with the articulators. So this is where we start having some differences between the vowel ah and the M consonant. So in this instance, the velum is actually open because it's a nasal. So air is going through the nasal cavities. So that's a big difference between the ah and the sound. The vocal folds are still chopping air as it's moving from high to low pressure. The pharyngeal cavity is open and the oral cavity is closed. So that's again another difference between ah and So with an M, it's classified as a bilabial nasal, so that's our output function. That's what we're trying to produce. The lips are in contact to close the oral cavity. So again, a difference between ah and And the reason that we need those lips to be closed is to redirect the air going through the nasal cavity this time versus coming out the oral cavity. And that's the difference between an and an ah sound production. Thank you for your time and hope you enjoy our project.